So earlier on in this course, in the physics unit, I kind of picked and chose what I wanted to cover, and one of the things I wanted to cover was electromagnetic radiation, different forms of electromagnetic radiation. And so hopefully this isn't entirely foreign to you. We talked about visible light is just one form of electromagnetic radiation. And then on the shorter, remember this, shorter wavelength, we have gamma rays, and on the longer wavelength is the symbol's lambda, we have radio waves. So we can actually get information from the stars. Kind of what I like to think of is that about the only information we get from the stars is this electromagnetic radiation. The only information we get from distant celestial objects is kind of this energy that's coming through space and time. So according to Wien's law, the star will emit electromagnetic radiation according to its temperature. So here over on the short wavelength side, we have the hottest stars, and over here on the long wavelength side, we have the coolest stars. Now notice that I've gone ahead or this figure has gone ahead and kind of made bigger this visible light. So with regard to visible light, and it's not entirely that simple, but your blue or white stars, okay, are your hottest stars, and your red stars are your coolest stars. There you go. Down here is something called a black body radiation curve. So it's sometimes a graph or a picture is worth a lot of words. So if, for instance, you take one of those hot stars, I'll pick on this one right here. K is Kelvin, so that's a temperature scale. So 15,000 Kelvin is the temperature of this star right here. So notice what this black body radiation curve is. This is just visible light right here. This is taking clear out here at shorter wavelengths, and it's saying what is the intensity of the information coming from that star at that particular wavelength. Okay, so that's kind of how that goes. I'm going to clear all my... So that's for a very hot star. Well, let's go ahead and pick the coolest star we have up here. Okay, the coolest star we have up here is 3,000 Kelvin. So it is the red one, the red curve. If we compare the blue curve for the hot star versus the red curve for the cooler star, hopefully you see two things. You see that the peak actually is a lot higher for the hotter star, and the other thing about the peak for the hotter star is it's farther over here into the shorter wavelength. And shorter wavelength means more energy. So I mean, it all kind of makes sense to me, I think. We compare the top of the cooler star, and it's right here, and the cooler star peaks over here at longer wavelengths, cooler temperatures. So I think that's pretty cool. Notice that our sun is kind of right in the middle. We're kind of like Goldilocks, and we're the, I don't know, the baby bear or something. Okay, so our sun is kind of right there. And I really like this figure because check this out. Humans, everything that emits heat or thermal energy, you can create a black body radiation curve for it. So our humans have this sort of little radiation curve. What does that mean? It means we're actually oozing energy in the infrared region of the electromagnetic spectrum. So I think that's cool. So to kind of, again, get away back from humans to stars, what does that mean? So now hopefully you can look up at the nighttime sky, and one thing off the bat, get a sense for blue stars are hotter and red stars are cooler. Okay. So another thing we talked about in an earlier unit, I think it was our unit on chemistry, we talked about electrons, and we said that electrons actually can give these what we call spectral lines. So these dark lines here are representing what the electron is doing. Okay. You see some elements: helium, carbon, iron, oxygen, etc. Okay. Now, what does that have to do with stars? Well, here we go. Actually, I mentioned that scientists, the best bet to get a handle on what a star is or what a star is doing is to gather electromagnetic radiation it's sending. And in looking closely at the energy we get from stars, we can actually see these spectral lines, what the electrons are doing around the gases associated with that star. And from the spectral lines then, scientists can actually map it back or understand a lot about the star. Let's just put it that way. So here, one of the things an important thing that scientists can get to is what is the surface temperature of the star. So these are all, let's see if I'm clear. These are ranked from, let's see, hottest to coolest star. Okay, that looks kind of like what our cool black body radiation curve was a little bit ago, in decreasing temperatures like that. So the surface temperature of a star is one of the biggest things that scientists use to categorize the star. And so what we do then is break them into what we call seven spectral types. These are spectra. They are stellar spectra because they come from stars. What are the electrons around the gas particles around that star associated, or what are they doing? So here are your seven spectral types. This is in order of hottest to coolest. Okay, and a mnemonic device to remember it is O, B, fine, guy or girl, kiss me. So O, B, A, F, G, K, M. Okay, that from hottest to coolest star.